and things work. Conversations, some of them beyond our imagination and comprehension. We're going to have Professor Brian Cox next, and he's going to be conversing with my colleague, Devika Chopra.
Thank you so much for that, Uday. Professor Brian Cox has graciously agreed to join us virtually. Professor Cox, thank you so much. It's such an honor to have you at the NXT Conclave.
Hello, thank you. It's a pleasure.
Professor Cox, without wasting much time, I want to ask you, what do you think will be the next big breakthrough in physics in the next decade? That's what people want to know.
It's a great question, and I'll probably be biased because I'll talk about the things that I find most interesting. But I think it's true to say it's an extremely exciting time. My research field at the moment is rather esoteric, so it's into black holes. And you might say, well, you know, what are the breakthroughs surrounding black holes? We know that these things exist. But in the last few years, there's a lot of excitement and interest in a field which is called emergent space-time. So the question is, are space and time fundamental properties of our universe, or space-time as Einstein would have called it from 1905 onwards? Is that fundamental, space and time? Or does space and time emerge from something deeper? And the study of black holes, which really began, I would say, seriously in the 1970s with work by Stephen Hawking and others that has been going on for 50 years, is now beginning to suggest that space and time are not fundamental. They emerge from something deeper, which is some kind of quantum theory. Now, and so you might say, well, that's rather esoteric, it's just interesting. What's very interesting is that it seems that there's a crossover between that research and research into quantum computing, and in particular techniques that we will need to develop to build reliable and even working large-scale quantum computers. So I think that's really fascinating for many reasons. First of all, it's overlapping into quantum computing, quantum technology, quantum devices, which are clearly one of the frontiers of technology and the most exciting areas of technology at the moment. But it's also, and I think this is really important, it's also a beautiful example of how asking curiosity-led questions in science about something as esoteric and seemingly distant as a black hole and how it works at a basic level can lead to deep insights into the structure of nature itself, but also can generate knowledge or transferable skills which are highly relevant for technological challenges that we face today.
Professor Cox, how do you see artificial intelligence impacting physics research? Do you think that it could help us uncover fundamental truths faster?
I like to divide that question into two parts, because I think clearly artificial intelligence already is impacting on the experimental side, data analysis. I mean, in my field, particle physics, we've used, even going back to the before AI, into neural networks and pattern recognition, we've always used that, because in searching these enormous data sets at places like the Large Hadron Collider at CERN, we need that assistance, we need that help. So there's that side of it, data analysis, and I'm sure that it will help there. It already has and already is helping. But then there's to me, the more challenging question, which is, could AI do what in theoretical physics, could it do what an Einstein did? Or going back further in time, Newton, theoretical physics, could it make advances in our fundamental understanding of the universe creatively? And the answer is, I don't know. I don't see why not. But I suppose there, we're getting into much deeper questions about AI, artificial general intelligence. Will these systems get to the point where they are outthinking us in a creative sense? Because ultimately, theoretical physics, theoretical science is a creative act in the same way to me that composing music, writing a symphony, or making great works of art is a creative act. And so I like to separate them, because I'm absolutely sure on the first point, even now, we are seeing AI impacting the analysis of experimental data. But again, that idea that it could, discover a quantum theory of gravity, it could help us with fundamental questions in all of the sciences. To me, that becomes the same. So I'd be interested to know what your audience thinks. We're then asking the question about the inherent, I suppose, creativity of an artificial intelligence system.
Professor Cox, I want to understand from you, what's the one concept about the universe you wish people understood more from your perspective?
I think there's a fundamental question. It goes back to the question you asked earlier, well, the most exciting areas of science. Another fundamental question, not the structure of space and time, but in biology, is life in the universe. So how common is life? How common is simple life? How far would you have to go from the Earth to discover another civilization? So complex life in the universe, how common is it? We don't know. One of the exciting developments, I think, in the next decade or so will be both the continued exploration of Mars and the search for life, maybe life began or still exists subsurface on Mars, and the two missions that are in flight now to Jupiter's, the Jovian system to Jupiter, and in particular focused on Jupiter's moon Europa. That's JUICE and the Europa Clipper mission. So they're in flight at the moment. We're asking the question, are we alone in the solar system? We don't know the answer. The answer may well be no. There's life on Europa, there's life on Mars, or elsewhere in the solar system. So that's number one. But then complex life, we don't know. We've looked a bit, we've listened with radio telescopes, we've heard nothing. In the history of astronomy, we've had no hint of any other civilization in the Milky Way galaxy, sometimes referred to as the Fermi paradox. It's a paradox because we've also discovered in the last few decades that I would say virtually every star in the sky has a solar system. So there will be trillions of planets in the Milky Way galaxy. The Milky Way galaxy has existed for the age of the universe, 13 billion years or so. So it is an interesting question. Why do we detect no sign of civilizations far ahead of us in the Milky Way galaxy? They might be there, but we haven't seen them. One possibility, which many of my friends actually in the biological sciences would say is the most likely answer to the Fermi paradox. One possibility is that complex life is extremely rare in a galaxy like the Milky Way. And I think that is a good working hypothesis. So your question was, is there something I would share about the universe? Mm-hmm. The thing I would share is that in my view, the number of civilizations in a galaxy like the Milky Way may be so low that you can count it on the fingers of one hand. It may even be, on average, per galaxy, less than one. It could be that we are the only intelligent civilization currently present in the Milky Way galaxy. And the reason I would share that possibility is that I think that makes us unbelievably valuable as a civilization, notwithstanding our physical insignificance. And I think the reason I say that's a good working hypothesis is I do think that if more of us internalize that possibility, that this is the only place where there are collections of atoms that can think in a galaxy of 200 billion suns, then I think that may make us have a rather different perspective on our value as a civilization. And so that is a message that I think I would love more people to take on board.
What a wonderful thought. Taking that forward, with space exploration expanding rapidly, do you think we will become an interplanetary species in our lifetime, Professor Cox?
I like the way you phrase the question, which is, will we become a multiplanetary species in our lifetimes? It's certainly possible. And so I would probably put money on it. I think probably yes. I would not have said that, I think, maybe 10 years ago, because the development of reusable rockets is a major step in allowing us to head to Mars. And it has to be Mars, by the way. I should just emphasize that there is no other planet beyond Earth that we could ever imagine even setting foot on, never mind building bases, other than Mars. Clearly, Mercury is hostile and too hot. Venus is extremely hostile and too hot. All the other ones are made of gas. You could imagine potentially, I suppose, visiting the moons of Jupiter and Saturn, but it's incredibly difficult. The distances are enormous. They're violent places, hostile places. So Mars, I think, is the only place within any conceivable timescale that we could land on and begin to build bases on. Can we get to Mars now with the technology we have? I would say yes, just about, but it is extremely difficult. It's challenging from a medical perspective, and that's where it's not the technology. I think we have that, but it's the idea that human astronauts can survive and thrive on what will be a 2-year mission at best, I think is very challenging. So I don't expect to see it within the next decade. I would hope to see humans on Mars within a decade or two. And then we come to the question of beginning to build bases on Mars and so on. But the thing I would say, though, is that ultimately it's absolutely clear that the opportunities out there beyond in near Earth orbit and beyond for industrializing near Earth space, which we've done essentially. If you think about communications and global positioning and Earth observation and so on, we already rely very heavily on the space above our heads, a few hundred miles above our heads. The possibilities to the moon, to the asteroids, and ultimately to Mars, to expand our civilization, access to resources, just the idea, which goes back to the early pioneers of spaceflight. I'm thinking about O'Neill and Zubrin and those ideas, those visionaries who wrote about this for a long time. The idea that we will have a new frontier in our solar system, in our civilization for the first time in a very long time, I think is extremely exciting. So I'm very excited about the possibilities, but both kind of more romantic in terms of exploration, but also just economic, the technological possibilities that are unlocked by our expansion out into the solar system. That's happening now and is exciting. But the specific question about becoming a multiplanetary species, that's more difficult. And I think we are talking decades in the future, at least, and probably centuries before we can claim to be truly multiplanetary, which means a self-sustaining branch of our civilization on Mars. I think that's many decades ahead, I would say.
Professor Cox, if we do achieve that goal of becoming an interplanetary species, how do you think that will impact our understanding of the universe? Because that would be the next goal.
Oh, I think I think it will. It opens up as our civilization expands and becomes more capable. Then the possibility to do science, just fundamental curiosity-led science, increases. So it could be to directly answer your question. It could well be that enables us to find life beyond Earth, and finding life beyond Earth, especially if there was a second genesis. So life began independently on Mars, a completely different kind of biology, then that will surely help us gain fundamental insights into biology itself. And so I think there would be tremendous benefits in the life sciences from having a separate example of life. So that's one thing. But also, space already has, of course, access to space has opened up a great deal of a tremendous possibility in our attempts to understand how the universe works, cosmology and so on. I need only mention instruments like the Hubble Space Telescope or the James Webb Space Telescope, or the Voyager missions to the outer gas giants. And a lot of our understanding of planetary science and cosmology, of course, has come from instrumentation that we operate in space. And so the possibilities for there are projects for large telescopes on the far side of the moon, for example. I think they're tremendously exciting, particularly in terms of radio astronomy, because you can do things that you can't do with Earth-based telescopes, and indeed telescopes in orbit in near Earth space. One of the possible missions that's very close to my area of research are the gravitational wave detectors, LISA, for example, which is a proposed gravitational wave detector that can operate in space, which could not only interrogate gravitational waves or detect gravitational waves from black hole collisions as we do now, but in much more detail, but begin to see gravitational waves, open up gravitational wave astronomy, for example. So those are just two examples. So I think the two answers are that space-based instrumentation has transformed our understanding of planetary science, of course, and cosmology, and will continue to do that. So I think the opportunities are, tremendously exciting.
Professor Cox, I also want to understand from a layman's perspective, how do discoveries in quantum physics impact our daily lives in ways people don't understand?
Well, quantum physics, it's often, I think, misunderstood in the sense that it's thought to be something that is just about how atoms work. And it's a thing that physicists do, but it's not particularly useful. Quantum mechanics, quantum physics is, it is fundamental to our understanding of how all nature works. All nature is quantum mechanical. It's not just small things. And the technologies that are already rely on quantum behavior or rely on our understanding of quantum behavior are, well, the transistor would be an example, right? So, or lasers and so on. So these are inherently quantum mechanical devices. But now the change is that we're beginning to understand how to manipulate quantum systems for our benefit directly. So quantum sensing, for example, building quantum sensors is something that we can do now. But quantum computing is, of course, in a sense, a holy grail. Quantum computing is really it's the technology to use quantum behavior, which, as I said, underpins everything, including ourselves, right? It's the way the universe works. But to use it to do something useful for us. Now, it's a very good question. But I should say, by the way, to answer your question, what would that do? What would a quantum computer do? Quantum computers, if we can build quantum computers that are easily programmed and controllable, then the computing power that unlocks, that's hidden in a sense in nature, is I think almost incomprehensible. It will allow us to do things with computers that would not be conceivable or possible, even with the most powerful classical computer we could design, given the entire age of the universe to perform that task. Quantum computers can, in principle, perform those tasks. And so they would, if we can build them, and we can program them and they work reliably. They could unlock an unimaginable computing power. That would transform society. Now, the big question, and many people in your audience will have views, there'll be many experts in your audience on this, in this field. The big question is, first of all, is it possible to construct a reliable, large-scale quantum computer? And you'll find different views on that. The general view is yes, it is possible. But the question is then, is it technologically, is it within our technological grasp in the next years or decades? And that's an open question. It's a very controversial question. There's a lot of money being invested in it from very big companies, and great progress is being made. But if the question of when we'll be able to commercialize that technology, when will it be genuinely useful for anything other than very specific problems, then the answer is that you will find very many different views. And so my answer, the summary would be, it is potentially, quantum computing in particular, is potentially extremely exciting. But when that comes online, the question of when it will be exciting is, it is, I would say, an open question.
Professor Cox, so what would you suggest countries like India should be focusing on? What cutting-edge infrastructure should be quantum computing, should be gravitational waves, particle acceleration, our own space telescope? What would you suggest we should be focusing on in India?
Well, I certainly think that building quantum devices, so having the capability to build qubits specifically, and to understand how to construct them, to build them, to build networks of qubits. I think that's absolutely clear that capability will be extremely important, and that clearly needs investment. As I said, whether that leads to an array of qubits that you would truly call a quantum computer, when that will happen, I think that's an open question. But it's clear that technology is going to be useful for very specific problems, if not general problems. So yes, the wider question, I think this is a very important and a very good question. My view is that because understanding nature at the most fundamental level is clearly important. Historically, it's been extremely important. And it's also historically been the case, and will continue to be the case, that it's very difficult to, I would say impossible essentially, to know which areas of fundamental research, which skills in your science base and your technology base and your industrial base, which skills will suddenly become necessary for a new technology or for some kind of new capability that will be extremely valuable or even vital for a country. It's impossible to know pretty much. So that might sound rather sort of upsetting to policymakers. It's like, well, how can we know where to invest if it's very difficult to know where the investment return will be? There is an answer, though. For me, the answer is that a broad and healthy scientific base, which goes all the way through your education system. So education, I see it sort of funneling into the universities, the research institutes, investing in a broad capability, investing in people, investing in skills for the individual. I think that's the way that you do it. You have to do it that way. So you mentioned particle physics, for example. So most of my career has been working in particle physics at laboratories such as Fermilab in the US, CERN, of course, in Geneva. CERN's contribution to society as a whole, to global society, it's been knowledge. It's fundamental knowledge, the Higgs boson, for example. Going all the way back throughout the history of particle physics, we're talking about the basic understanding of the workings of the universe. That's a tremendously valuable thing. But if you say, what are the contributions that CERN has made beyond knowledge? Of course, they're immense. The World Wide Web being the most famous example, perhaps. But medical imaging technology, the use of particle beams for cancer treatment and in medical technologies and so on. You could go on. Materials science. It always turns out, and I emphasize, I said it before, that the trying to understand how nature works at a fundamental level can have consequences or open up opportunities that we could never have imagined. And so you have to invest in a broad science base. If you have a broad science base with as many people working on as many diverse problems in all of the sciences as possible, then your country is ready to take advantage and to invest in and to benefit from any discovery that's made anywhere in the world. And that's so. I know that when I speak to government, for example, in Europe and the UK or the US, and you say things like that, that it's well, no, but surely we just tell us where to invest. I genuinely believe that nobody is smart enough to know where the next revolution will come from. Just to finish, I see research, university research, and industrial research as my picture is that the researchers are like little ants, sort of wandering around randomly on the frontier, on the edge of knowledge. And so we stand in this terrain which we understand, and we look out across the horizon into the terrain we don't understand. And science is really a random walk. History tells us that. And so really, the more ants you have scrambling around on that border, making random, taking random routes into the unknown, the more chance you have of finding, essentially hitting the gold mine, in discovering knowledge that is transformative to our societies and to our civilization. So my recommendation is, if we possibly can, just have more ants.
Amazing. Professor Cox, what role do you see India playing in the next generation of scientific discoveries and in science?
Oh, I see India as being transformative. Of course, historically, India has been a big player, and will continue to be so. But you look at the heritage of in space exploration, for example, ISRO. There is a space agency that's been operative pretty much since the beginning of space agencies, right? Certainly since the late 60s. And so the ambition to build the space stations, for example, you might say, well, why should a country like India have the ambition to have its own space stations?
Yes.
It got everything I've just said, if you think about it. The idea that you're investing in the skills and the technology, and you're investing in a laboratory that exists on the frontier, it should be clear from what I've just said, my view of how technology and science advance, that's vitally important. So I think it goes without saying that countries like India, which have not only the heritage, but the potential and the current capability to advance human knowledge, it's clear to me that there's a central role to play.
Professor Cox, you've also visited India twice before to witness a solar eclipse. What can you share with our audience about that visit, very special visit to Varanasi?
You know, in Varanasi, the solar eclipse, it was one of the most powerful experiences of my life. First of all, because it was in Varanasi, which everyone will understand there is no better place on earth to experience a solar eclipse than Varanasi. And my memory of it on the banks of the Ganges was that I think there were over 1 million people gathered. It was a huge sort of crowd of people. And but what I wasn't ready for was that it was quite cloudy at the time. And so we were stood there with a 1 million or more people waiting for the eclipse to happen. And then the clouds opened just at the last moment. And the strange thing for me is that as the moon begins to cross the face of the sun, you get a very fast sunset, essentially. It goes dark quickly. And the silence, the crowd, this huge crowd sort of goes silent, almost in awe. And what I felt very strongly, for the first time in my life, I felt that I was standing on a ball of rock orbiting around a star in space. And I don't know why I felt that. There's something about seeing the moon So this obviously this spherical thing cross in front of another spherical thing very quickly, and the night falls extremely quickly, and silence descends, and you stand there and you realize that you're on a spacecraft with all these people, these millions of people, all the humanity surrounding you that is silent, watching this thing happen. And then the moon sort of leaves the sun. You get the very famous Bailey's beads, the so-called diamond ring. And then there's an eruption of noise that, as everybody sort of cheers. And you think, what is everybody? What are we all celebrating? And I suppose I got this sense, especially being in Varanasi with its tremendously rich history, I got a sense that we were celebrating humanity itself. And our presence, our very existence in the universe. That's what the feeling that I got. So it was one of the most profound and powerful experiences of my life.
Professor Cox, I sure hope you'll be back soon, but before we let you go, you're an advocate of curiosity and wonder. What's your advice to someone who wants to think more like a physicist, even if they're not working in science?
My advice would be that it's all about, you used the word, it's about a sense of wonder. It's about paying attention to the smallest things and asking questions. And it can be a very simple question. It could be, why is the sky blue? Why are leaves green? Why is the grass green? It's a tremendously interesting question. If you want to understand why the grass is green, you find out that there's chlorophyll and there's this pigment which is associated with photosynthesis, which goes back to some of the earliest complex life on Earth. In fact, some of the earliest cells on Earth. And so in every blade of grass, the entire history of life on Earth is written. And so it's that idea that the simplest thing, the simplest property of nature, whether you're looking at the stars at night or the Milky Way, or you're looking at grass, you're looking at an ant crawling across the floor in your house, any of those things contain wonder, have the possibility of generating wonder and awe. And if you can hold on to that feeling, then then you are a scientist.
Professor Cox, what an honor it's been to be in conversation with you once again. Thank you for joining us at the NXT Conclave. Thank you so much for being with us. We sure hope to host you soon.
Thank you very much.